All right, so the one last thing that I wanted to go over with the four principles of experimental design is who exactly does this study apply to? So even though we've created an experiment that we're allowed to do inference on, which means we can make conclusions about the larger population, it's only going to apply to male physicians just like this one in the study. So if we take these results and apply them to females, it doesn't really make sense because they weren't included in the study, so we can't make any conclusions about them. All right, so now the question is, we've looked at placebos, we've looked at the vocabulary. How exactly do we design an experiment? All right, so most of the time I think it's easiest to do a diagram. However, if you would like to write it out in paragraph form, that's totally fine. So let's just take a look at our 50 SA2 students and create a completely randomized design. So here's what you want to think about when you're doing this. Number one, you want to think about how many subjects or experimental units did you start with. You want to make sure you're explaining where you're randomly assigning. So when are you randomly assigning that treatment? How many is in each group? And then you want to decide what is the treatment within each group. Finally, you want to make sure you state what are you going to measure. And in the end, you're going to end up making sure that you are very specific about what you're measuring. So notice right here, we said how many we started with, 50 volunteers. Now, this RA is short for random assignment. We're randomly assigning them to two different groups. The two groups is the online group and the classroom group. Notice how I have the number of students within each group. Your goal is to make these about the same size. And then these arrows at the end mean at the end, we're going to measure and compare SAT scores. So we're going to compare the SAT scores of the online group to the classroom group. Now remember what this random assignment does is it allows groups with sort of the same variability, which just means that I'm going to get students that like online learning, don't like online learning in both groups, AP students and non-AP students in both groups. These groups are to be as similar as possible so that we can ensure that it's the treatment that's working and not some other lurking variable. Now, please make sure you include how the random assignment will take place. If you don't, you will not earn full credit. So when you say randomly assign here, someone should be able to read this, and we talked about this previously, but you want to explain how that random assignment is going to occur. All right, now that you have your experiment, how can we show how the random assignment will occur? Now, we've done this before using the hat method, using random integers, using your calculator. So here's one example. This is putting 50 names of students on identical pieces of paper, put their names in a hat, shake it up, pull out the first 25 names. Now notice how it states what group they're going to. They're going to the online group. The remaining students will be in the traditional classroom. A couple key things here. Make sure you're stating identical pieces of paper and well mixed. And then please also make sure that you are stating which treatment group each are going to. Don't just say like 25 will be the first group and then the next 25 will be the second group. Specifically state what groups they're going to. Now the question is, could we do this with the toss of a coin? No. Why can't we do this with a toss of a coin? Well, we have 50 students, and if I toss a coin and I say heads is online group and tails is the regular classroom, theoretically I could get 50 tails, which means every single person would go into the regular classroom. So that wouldn't necessarily make sense, and there's also no way to guarantee that each group is going to have the same size. So I could end up with 30 in one group and 20 in the other, or 10 in one group and 40 in the other. So tossing of a coin is not going to work in this case. The only time you use a coin toss is in matched pairs, which we'll talk about later. All right, so I want you to go ahead and try one. Go ahead and read this. So go ahead and try it, and then on the next slide, you either have two choices. You can do the experimental design, or you can, like how I did with the diagram, or you can actually write it out. Just make sure that you're always including how you're going to randomly assign, because that helps to reduce bias. All right, so let's see. Did you answer your questions correctly? How many children? We started out with 60 children. Where's the random assignment taking place? At the very beginning, completely randomized. All right, we're doing 20 children in the fast pace, 20 children in the slow pace, and 20 children in the drawing. This is to help reduce bias. And then at the end, what are we going to compare? We're comparing the mental ability and impulse control. Don't just say compare, because if you say compare and somebody's reading this, they have literally no idea what you're talking about. And then this right here, notice this was not included in the directions, how the random assignment will occur. or will take place, but you need to include that. You have to understand that that's just automatically part of the directions. So here we use 60 equally sized slips of paper, label 20 the slips 1, 20 the slips 2, 20 the slips 3. Notice, mix it up. Have each child draw a number without looking. All right, the number that each child chooses will be the group that he or she is assigned. At the end of the study, compare the mental ability and impulse control for the 3 treatment groups. So you could say the 20 of them were going to the fast pace, the number 2s were going to the slow pace, and the number 3s were going to the children that were drawing. All right, so go ahead and try this question. So this is talking about music students. So you're going to outline a completely randomized design for this experiment. This is drawing your diagram. And then make sure you include how you'll carry out the random assignment. Make sure that if you handed this to your classmate, that they would be able to randomly assign the students to the various treatment groups, and then make sure you answer the question, what's the purpose of the control group? Because we always want to have some sort of control group in our experiment to compare against. If we don't, then the experiment isn't necessarily accurate or reliable. Okay, so the question is, did you include 29 students? Did you include the fact that you were randomly assigning them to the small group or alone? Now notice these 2 groups aren't exactly the same, but they're very similar in size, okay? So your goal is to get them very similar in size. Obviously that can't always be true if you have an odd number of participants or subjects. And then finally, what are you comparing? The accuracy of final performance evaluations. If you feel like writing it out in words, that's totally fine. Notice the random assignment is there. Use 29 equally sized slips of paper or identical pieces of paper. Label 15 small group, 14 of them alone. Shuffle the papers and then hand them out at random to the 29 students to assign them a treatment. So we're reducing bias and trying to get these 2 groups as similar as possible. Now, what is the purpose of the control group? The purpose of the control group is a baseline for comparison. If we just do the small group, what do we have anything to compare it to? Without a group to compare it to, it's impossible to determine if the small group treatment is more effective, because we're comparing the results at the end to see if the small group basically did better than the group that worked alone. All right, the logic of a randomized comparative experiment depends on our ability to treat all subjects the same way in every way except for the actual treatment being compared. So pretty much our goal is to treat all subjects exactly the same. So in order to make sure you have created a good experiment, you want to pay careful attention to details to ensure that all subjects are actually treated equally. So that's having like the placebo and the drug exactly the same. As much of the environment that you can control for as possible so that everybody's treated exactly the same. Now, when you have, let's say that we have the people that are taking the aspirin versus the not aspirin, when you have a response to a dummy treatment, it's called a placebo effect. The strength of the placebo effect is a strong argument for randomized comparative experiments. So for example, if somebody is taking a drug for diet and they're testing diet pills, and one group knows that they have the diet pill and the other group knows that they think they have the diet pill, they can potentially maybe lose weight literally just because they think the pill that they have is a diet pill. So the placebo effect means that they're like losing weight, but it might not necessarily be because of the drug. They think the drug is working even though it's not. Maybe they're just eating healthier because they think they're on a diet drug. Okay, so why do you need a placebo? When you're designing an experiment, you want all subjects to be treated equally. If you're giving pills in a medical experiment and half the groups takes the pills and half doesn't, then they're not all treated equally. So this is just a quick example of the placebo effect. So remember, when you're a child, you fall down, you get a boo-boo, and your parent gives you a kiss. It's not really an active treatment. It's basically like a placebo. You are feeling better even though you didn't actually get a treatment to feel better. Messes with your mind. All right, so this is actually interesting. So 60 Minutes aired a segment about the placebo effect. So if you want to take a minute and check out that video, it's actually it's just a quick, interesting video. So what happens if you're the doctor administering an experiment? Are you going to expect less from your patients receiving the placebo? Are you going to interact differently with them? So the question is, how can we avoid this? How can we avoid the placebo effect? Well, one way to do that is to have something called a double-blind experiment. What is a double-blind experiment? That means neither the subjects nor those who interact with them and measure the response variable know which treatment a subject receives. So what that means is if you are the doctor that is looking at the effects of whether the drug worked or doesn't work, the doctor themselves don't know who got the treatment and who did not, and the patients don't know who got the treatment and who did not. So that's double blind. That means then when they measure their response, they're just looking for a response. They have no idea who got their treatment and who didn't. That's double blind, and then just the researchers sort of behind the scenes, behind the glass wall, would know which patients got the placebo and which got the regular drug. All right, so let's just take a minute and think back to our caffeine experiment. How could we do this so that it could be double blind? Number one, we have to make sure the colas look and taste exactly the same. So the people measuring the pulse and interacting with the subjects should be unaware of who's getting which treatment. The subjects also should not know who's getting which treatment. They shouldn't know whether they're drinking caffeine or caffeine-free cola. The subjects can measure their own pulse, all right? This makes it blind because they don't know which drink they got. So they didn't know which drink they got, and they're measuring their own pulse. So that's essentially a double blind experiment because they don't know anything about the treatment that they got. Now, here's the tricky part. Someone must know what drink they received. So it's not really double blind. It's just double blind in the sense that the person receiving the treatment doesn't know whether or not they got the treatment, and the person measuring the response doesn't know who got the treatment. As long as there's somebody in the background, okay, who does know who's getting their treatment, it's still considered double blind. As long as they don't actually interact with them, they're sort of watching behind that glass wall, it's considered a double blind experiment. All right, most experiments are usually single blind. Sometimes it just makes it a little bit easier because it can be difficult to do a double blind experiment. What if we're comparing two different exercise regimens to decrease our marathon time? So if you have two different exercise regimens for group 1 and group 2, then obviously the people that are doing the two different exercise regimens are going to know which exercise regimen that they're doing. So this is considered a single blind experiment. So maybe the people that are looking at the results at the marathon time, they don't know who got the treatment. So the people that are measuring the response don't know, therefore that's single blind. With a single blind experiment, the individual interacting with the subjects and measuring their response won't know who got which treatment. So at race time, they're going to compare the results of the marathon, but they won't know who got what training schedule. So the participants knew what training schedule they did, but the person measuring the response did not. All right, so go ahead and take a minute and read this and answer the question. So after reading this, you want to answer, did the experiment design take the placebo effect into account? And why is this important? Was this a double-blind experiment? Why is this important? And based on your answers to question 1 and 2, how could you do an improved design for this experiment? Okay, so number 1, there was no placebo effect. The mothers who saw their unborn child could possibly encourage them to eat a better diet, resulting in healthier babies. So they saw the ultrasound. All of them saw the ultrasound. Was this double blind? No, this was single blind. Why? Because the people weighing the babies at birth may not have known whether or not the mother had an ultrasound, all right? So it was single blind because the people measuring didn't know, but the mothers knew who had the ultrasound. So this might have affected the outcome because the mothers knew whether they had received the outcome or not. Now, how could we improve it? The way to improve it would be potentially to make it double blind. We're going to treat all mothers as if they were having an ultrasound. However, for some mothers, the ultrasound would not be turned on. You're saying, how would this work? So in order to prevent that, mothers from knowing whether or not it was turned on, the screen with the baby would be turned around away from the mother. So every single mother would get an ultrasound, but the screen that's showing the baby would be only facing the person doing the ultrasound. It wouldn't be facing the actual mothers, so they wouldn't know whether or not the ultrasound machine was turned on. Okay, so it's just a funny comic regarding the placebo group. All right, so go ahead, and whenever you're done with this one, you can watch the next video.